Okay, so hey everyone. Today we have the pleasure to hear from Galin Gyulchev from Sofia University. Galin is an associate professor there, and he will talk to us about visual signatures of scalar hair in the images of accretion disks and shadows of rotating black holes. So feel free to ask questions during the talk. There will be time also at the end. And Galin, thanks a lot for being here. You have the floor.
Thank you very much. So first of all, I want to thank for the invitation. So it's really an honor and pleasure to be here in your group because I'm really very inspired by the work of all this study which you have about the Galin constellations with stellar care. So really, it's an honor to be here. How this part of my study begins? So, for example, I tell you only a few words. So, when I was a PhD student for the first time, I started to study what is happening with the shadows of the black hole solutions. After that, a little bit, I start to realize what is happening with the direction. This for the first time, maybe 10 years after that, I realized how we can perform really the shadows and after that make the operation distinct to the carrier positions with stellar care. So this was really very amazing thing which I didn't believe at all that it is possible to be done. Yeah, but fortunately, I realized that this is very interesting topic. So because of this, both of the very strong impact over the observations, we believe that this color air can affect. We are inspired by your work, and we decided to find not only the shadows, but to find the images of the integration disk. In this case, black hole solutions with our care. So this is the examination which I'm going to show you today. Is based on our collaboration with one field student from Kliment University. It's together with Daniela Autonomous, so if you have here. So Daniela is from Kliment University. Today it's researcher there. Sofia is from Sofia University, and also is from Sofia University. So we together are going to examine this phenomenon. Okay, so every one of you is familiar with what is gravitational lensing, so it's not necessary to explain what is happening with the deviation of the light rays in space-time around the Kepler, for example, and so on. But just let's make a short overview why really this is so important. So first of all, we know that if we study in general the gravitational lensing around rotating black holes, we can extract information about the mass of the object and about the angular momentum of rotation. And if we generalize our attention not only over the bulk of the objects which possess a black hole horizon, we can extend this our understanding and reject the lensing phenomenon of horizons as object, which as for example have the naked singularities and wormholes, and to understand what is happening with the gravitational lensing effect, and more especially to examine the shadows and the rotation disk for in general hypergration disk, for example. Those hypergration disks are a very complicated topic because it depends very strongly from the model of the disk. So we are going to restrict our attention today only over the shadows and the integration disk. So because it is, it will give simple understanding and very good and I believe very precise intuition what is happening with all the problems which we have to understand before continuing to further in the integration test. So finally, all this problem became very important after the simulations of the image of the center of the galaxy is M87 and the image of the black hole center of our galaxy were motivated to extend this examination and to involve the scalar fields, which can modify the understanding which we have about the gravitational lensing from general relativity. So because of this, if we consider only general theory of relativity, but not traditional scalar fields, we not are going to modify it itself. But for example, we can use the scalar field as an instrument, for example, to model dark matter in the different scales depending on the mass of the scalar fields. So, for example, we are going to see after that, and probably even not from the start of the there, that when we have a scalar field with a huge mass, it is going to disappear very fast linear part of the horizon. But when the mass of the scalar field is really small or almost is equal to zero, the propagation of this scalar field can be observed very far away from the black hole horizon, which means that it really can be used as an instrument to model dark matter in different scales. So, because this we are going to understand and to explain the images in this one. For example, here we can see the image of integration test, which we believe that it is operation disk, and inside the operation disk we can see the shadow. So how probably will look the shadow in this situation, in this case, and after that I will explain how we can obtain these images. So in order to model these images, we consider a multiple scalar fields, which are minimal coupled to Einstein gravity. Where, for example, this V is the potential scalar field which we are going to show after that. But using this general form of the action of the theory which we consider, we assume that we have multiple scalar fields which can serve as instruments to construct the so-called target spacetime, which is in this case three-dimensional space in which we can model the curvature of the space and use the curvature of this space as an additional parameter in order to understand how it will impact over the images parameter. So, taking into account this action, we finally obtain this Einstein equations, and this equation which will govern the behavior of the scalar fields, where this gamma, this gamma AB is the matrix of this so-called target space. And by this metric, we are going to use after that, taking into account some additional symmetries, what is the curvature of this target space. Okay, so inspired by the work of Professor Federo and Eugene Verdu about the also scalar here, we restrict our attention only to two scalar fields. Because we want to imagine that we have only one effective complex scalar field, which can be modeled as two real scalar fields. So this means that exactly in this situation, we are going to restrict the attention over these two scalar fields, but we are going to introduce the Gaussian curvature of this target space. constructed with these two fields. In this way, we're taking into account the symmetries and representing the metric in this form, the metric of the time space in this form. We can introduce the Gaussian curvature of time space and to introduce it as a boundary. So the potential is chosen to be in this form here, where C is the mass is the found in the star fields, the mass of the star field, and every one of the observations of the observational quantities which we are going to consider hereafter will be taken for the arbitrary mass fields. Okay, so finally, in order to examine the gravitational length of this theory, we assume that our black hole solutions can be described by this partiality symmetric form metric, where this coefficient n here is the only coefficient which is known analytically. H is the black hole horizon, and L1 is the coefficient here of the function f 0, 1, and 2. And are numerically things, and they have to be interpolated somehow in order to make the dimensions. So after that, we have to restrict again our attention fixing some of the parameters of this curve. So the major thing is that we assume that this curve is oscillation frequency omega s, which in our case will be equal exactly to the circular velocity of the oscillations of the black hole horizon in the limit when we go to the black hole horizon. And in this way, we believe that this curve field is synchronized with the black hole itself. So because of this, we're going to use we obtain finally that the frequency of the rotation horizon is directly related to the frequency of the observations in this form. So this solution which we are going to examine can be considered here in this well area, and we choose. Also, because we are familiar with this parametric space, I believe that it's not necessary to explain it carefully what we see here in this picture. But for example, we know that this black one here represents black hole solutions. Here with this green one, for example, we get the X amount of black hole solutions with star here. But we are going to consider only this well area here. Here we can see with the dash point, we can see the solutions of the character calls here with constant radial horizon. And the other important truth is that every one of these solutions characterized with some other important point, which is called normalized charge. So this normalized charge represents what is the amount of the angular momentum of the scalar fields with respect to the angular momentum of the configuration. Okay. So this quantity gives us a very good intuition how to compare the different solutions, because if we obtain some image, for example, we have to check really what is happening with the impact of the headings of the solution over the images. So this actually is very useful for here. And in order to explain the lensing, we are going to consider this general axial symmetric form. We are going to calculate all these equations of the geodesics and introduce this general form potential for the particles in the form, especially these particles. And because we first of all we want to examine more especially the equation, this and how this equation is created. So we are going to apply the conditions or the potential over this over the function with potential, because what we want to understand. So in order to imagine that the equation this exists, we just have to check out their existence of circular orbits in this geometry which we found, and to find these conditions over the potential, we can understand how there exists a circular orbits. Okay, but solving this system of equations for the effective potential, we obtain this these restrictions over the integrals of motion, the energy, and the angular momentum of the particles. And because of this, we find after that an equilibrium velocity of the rotation of particles over these orbits. We obtain all needed tools or instruments over which we can understand the destiny of the particles inside this configuration. So this means that we can understand how the pressure of these orbits are stable or unstable, and finally to understand where the innermost stable orbits, which means that with other way we can understand where is the inner ends of the rotation disk and where is the outer end of the rotation disk if it exists. So in general, we know that for this metric and for this effective potential, it is asymptotically goes to zero at infinity, which means that in general there exists stable circular orbits at infinity. So most of these here are the and finally, in order to obtain this orbits, we apply the restriction as the second real state zero. We obtain this non-linear Descartes equation. But finally, we can understand clearly what is the geometry of this. Okay, but here after start the interesting parts, because this accretion disk is not uniform accretion disk, so it doesn't have inner part and outer part. It can be split into different areas because of the fact that the orbits probably are not stable there. And if we put the part from this part of the accretion disk, it will not going to rest there over the circular orbits. It's going to be falling down, or it's probably going to skate away. And because of this, in order to check the stability of the orbits, we check the equilibrium velocity of the accretion particles, and we see that it doesn't possess its own simple structure. So we have a different information here, which became more complicated because of the existence and of the additional parameter of the calcium curvature. So for different normalized charges, we have some kind of behavior, but the calcium curvature made things more complicated. And because of this, what is the most interesting thing here, that we can observe two different major situations. On the one, there is that for some parameters, the angular velocity of the rotation possesses this one here. So, for example, the red curve are the outer, the so-called concrete orbits. But we obtain a second rules of the particles, which again are concrete particles. And the interesting thing is that the discriminants of the equation which describe the angular velocity can become complex, which is exactly the same situation here. So that situation is this: if when this discriminant is a real number, we have the touching or interaction with this continuity here of the function with omega. And we observe two different regions. So this bar here, which is on the right hand side, and this bar here on the left hand side. Because of this, we can believe that the accretion disk can be split to two different parts. So we have outer accretion disk and inner accretion disk, where the orbits can be put and to be populated there. But In addition, if we examine the effective potential, we can obtain that multiple curves are possible if we want to obtain stable quantities. So they are stable only here in the deep lines, into the solid lines, but here in the dashed lines represent areas where, for example, the second derivative potential in this equation is positive, and this means that there is no existence of stable orbits there. So all these equations make the picture very important because we understand that this can possess very complicated structure. After that, when we have this equation, this is over here after we can bring the interpretation of the density itself, because if we believe that the particles beside this expression gives wider one with respect to other, or we have from other point of view charged particles which are located there, and because of direct magnetic emission, we can have emission quite. So we can examine the relational density and what is happening with the observational quantities related to this emission. So because of this here, we following the standard procedure. We can examine the shells and the equations and how they will look like. So this here, the same which I didn't know. So we use the equation quantum equations. We introduce those zero potentials, and after that we can migrate the basic into this black hole configurations. So the next thing is that this space-time configuration possesses not only two white rings, which is one of the major characteristics of the Kerr black hole. So we know, for example, that the Kerr black hole possesses photons which can move cooperate and retrograde on different circular orbits, which has a radius which depends very strongly on the angle of the atom. And here, in order to explain what is happening here, if we introduce the effective potential of the photons, and we apply the same restrictions of potentials, we can obtain the general equations which will give us some information where in this space-time there is stable or non-stable circular orbits of photons around the object. This is very interesting. And following this procedure, for example, we can visualize the potential particles that are from zero potentials, and examining other points, in the external points, we found out that in this configuration there exists 4 white rings where they have the next stability. So this is the outer line, it is still stable. The second inner line is stable. This here. So this is unstable. Yeah. This is unstable. This is absolutely stable here because it is stable in the other direction. In the direction of the innermost is unstable. So because of this existence of these white rings and the existence of a stable white ring, we see that because of this third one stable white ring, we can assume that when the photon hits this white ring, they will follow these white rings very long time, which makes the integration of the equation very hard. So if you put some field parameter to integrate this orbit, it will go to integrate the orbit until the finishing of the field parameter of this, which really is not good, but this really prove the resistance of stable batteries. So after that, considering the fundamental of the photons and using these useful parameterizations, this will plus literal, which maybe was introduced for the first time from yeah. very easily we can perform ray tracing and to make mapping between the integrals motion of the photos and the observable volume. So it's really very easy to get it done. And here, these are this X and Y, for example, quantities. Okay, so then making this, if you want to understand what is happening here, so let's first see this picture here. So in order to understand what is happening here, I just visualize one of the points, this purple here, and I choose one line, so for example, for this point, and both of the here you see what is happening with the red tracing and how this white tracing interact with the white rings with different white rings which are stable or unstable. It's very interesting to understand how this ray tracing actually leads to this picture of shadows. So, for example, in this picture, in this orange rings here are the unstable white rings. We see that because of the geometry, we have different channels. So, for example, here we have one white that is the channel, and it's one preference down channel. We describe these different very strange parts of the channel from the right hand side. Okay, and in order to understand the behavior of these white rings, I will try to
Sharing them Zoom, please.
So you see here that if you take this plane of white rays, which will pass the rays source, and we are going to deviate the direction of this plane, you can see how slightly changing of the initial conditions of the white ray, considered over the source, can lead to a healthy behavior of the geodesics. And this is happening because of the finding federal about the fact that the existence of stable white rings is very strongly related with the healthy behavior of the objects or the photosensitivity. For example, if the healthy behavior, probably there exists a stable white ring. And this is really what we can see. With the very slight change of the initial conditions of the photos, we get very strongly changing of the behavior of the geodesics. And in a very good way, you can see the different channels, how the number of the channels which hit the horizon, these blue lines, how they change, and we can understand how really the form of the shadow has been created in this way. I need to share again presentation.
Can I ask you, for this case, what's the curvature of the target space? What is your shown?
I think it was -5. -5, yeah, it's not 0, it's -5.
Do you see qualitative differences with the variant curvature of the target? So is this one able to zero there?
Yeah.
Singular dimensions.
So the when you change the Gaussian curvature, the structure of the white rings is not changing. So they move a little bit. One of them became a little more wider, the other ones maybe a little more drift. But this structure is not changing, but the shadows are changing. And we are going to see after that over the pictures how this changing this happened when we changed the Gaussian. So for example, some shallows became a little bit more shrink and more smaller area when the Gaussian curvature increase. And this is the missing part here. The new part. Yeah, so in general, there is changing, but over the structure of the white is unfortunately not. White didn't observe. So this what you call the sample white topology, which is very interesting here. And I think that according to my study, with this only three values of the Gaussian curvature, minus 5, 0, and 5, I didn't observe change in the structure. Okay. And now if we are going to consider the observation of this observation, this here following the simple procedure of the node and the so in this model, what is the most simple assumption that the mass transfer into the relation into the area of the relation. This is constant, which is I believe not so real, but it's very good approximation to assume that the mass is not changing in time. So then if we know just the integrals of motion, the energy, and the improvement of the path when the capital goes to the computation, we can calculate using this formula derived from one of the and shown the paper of Thorne and Page, I think. So we can use this formula for the radio emission of the lights inside from this and after that, in order to understand what is happening to the observation of books, you can involve in the redshift because the capable the loss in the computation of the particles. And so we
Can I ask a question? You mentioned that there can be disconnected regions with several. So in that case, you integrate over different regions.
It's a very good question. Yeah, because we have very different parts of the equation. This hereafter we study only the outer parts of the outer solution of the innermost layers of orbits to some higher values, which we know that there are existence of this, but the internal parts which are inside, they can be very with a very small area. So the inner and outer part of this are very close to one another. We will not take the example then.
So your integral is not from our ISO, but from our outermost marginal circular orbit to some rate. Is that what you said?
It's in general from the outer solution of the historical orbit.
Yeah, but ISO is the innermost. So that's the marginal, but it's not the innermost.
Yeah. When the energy is equal to 1, we can derive the yeah, so here, if I take to be over, there is some problem. If we consider the capillary velocity, we can obtain the maximum inside, which is above the historical orbits, and this maximum didn't give us opportunity to calculate this problem here into the right way, because this formula gives a negative flux, which is very strange. So when the derivative here is negative, this factor in the front of the integral negative flux will be a negative, which is not possible in general. And there really we can be very more careful. Where actually using this model, we can choose the inner part of the equation system. Yeah, but in general, taking this assumption for the east solution and for the marginal orbits, we calculate this process after that. Okay, so we have made Here I present the variety of different radio emission of this. So every one of the screens again information from from three different Gaussian temperatures. So we have three curves. The red one is for positive Gaussian temperature, the black one for zero Gaussian temperature, and the blue one for negative temperature. And the more interesting here is that for the variety of normalized charges, so in every one of the pictures, we see that in every one situation, the red curve is above and the green curve, is below, which is interesting in order to understand how the Gaussian curvatures impact the observational characteristics. So this means that there exists combination, for example, this picture here, there exists combination between the charge, and the curvature, for example, this curve, which shows, for example, in this picture, that we also can observe a maximum emission in all these configuration which we found. After that, in order to show what is happening to the imaging, performing the latency procedure. So we see that for different normalized charges, the disk in general looks in a different way. So, for example, here this is for very huge normalized charge. So this is a charge which we almost reach the solid atomic solutions. So this black hole which we have in this equation is with almost the maximum value of normalized charge, which is very close to the bosonic saturation. So it also the shadow is very tiny, so it's almost disappears. If we make this transparent, we can see the internal structure of the shadow itself. So we see a lot of different parts which are detached to 1 meter spectral. And we can assume that this is not simply connected, which is very difficult to display. Here, also, we see that we expect this of the shadow. So after that, when we change the Gaussian curvature to positive, so this picture changes a little bit, and yeah, so we can see that these black parts of the shadow became a little bit more shaded. And when this is done, again we see the changing. And when the Gaussian curvature is positive, so we can see increasing of the flux, but the shadow became more shrinking than the previous situation. And the additional thing is that here we see some center of vibration. So we have some fluttering flux, which is not observed in the mechanical pulse switch. So the flux is distributed in a different way.
So when you're comparing the different Gaussian curvatures, you are fixing the little cube, the three values that you are considering. Is that what you're fixing? Yes, but the mass in the hair varies. So from your positive K, like 0K, and negative K solution, they have a different mass in the scale. Is that correct?
Probably, yes. So we fix only the normal.
You only fix the angular momentum.
Yes. So because all the quantities are factorized with respect to mass or considered in the units of mass of the field, therefore orbital mass. We just assume that they are in the units of mass. Yeah, so because the number of the parameters is very huge, we realize that in order to make the comparison, we just can choose for different Gaussian curvatures solutions with almost close values of the normalized charge in order to understand how they can be compared. And after that, to change the curvature of the target space time, you just see it. Okay. Yeah, so after that, so here, for example, we can see that the shadow is going to increase a little bit, so the housing furniture leads to a little increase from the shadow when this charge is very high. But after that, if we decrease the charge, so if we are going to decrease the charges, the dark area became more higher. The structures became more higher, but still we can observe the positive behavior of the point because we get the same light in this configuration. And we increase the condition. Yeah, you can see it. So this black part here is going to really change the structure. So the complicity in general, when the curvature becomes higher, for some value of my charge is going to decrease a little bit. So the increase of the curvature is going to calm a little bit the complicity of the behavior of the parts. So this is really interesting here. And after that, again, I continue to decrease in the charge. You can see again similar behavior. So for more current also, we can do again. And when we continue to decrease the charge, we can see definitely that the shadow became more wider. So the area is going to increase. And again, we get this different part of the charge. For example, here, I just have to mention that when the charge is not high, but it possesses some middle values between 1 and 0, the behavior of the curvature is not the same as when we have very high values of charges. So it's in the middle of the values of the charge. The curvature is going to make the shadows to be more trimmed. It's not the same as when the charge is very high. And after that, continuing this procedure, we start to see that for small, really small charge, this electricity start to disappear because we didn't have stable lighting. So we have only two unstable lightings, which is the hair situation. But because of the existence of the scar field, the flux is a little bit higher than the source of the air solution. So the distribution of flux is not the same here. And the third thing is that the shadow side, this white, this observable white ring is very small with respect to the shadow border related with the care section. So really the impact of the scar field is very complicated here. Okay, continue with this thing. We can see from the different values clearly changing. So they became almost the same. So this means that finally, if we decrease enough the overall charge, the behavior of the Gaussian curvature over the observations doesn't impact us so much. So it doesn't. And finally, after this, I want to show 3 different panels for the channels. So this information here again is inspired by the work of Berkeley, because I see really in a very clear way he just changed the information and for different technologies discovered here, we can see what's happening with channels. So, for example, if this left column here is negative Gaussian curvature, and this right one is positive, so here is for 0 Gaussian curvature, and we can see that if here the inclination is around 20 degrees, which is the saturation of the inclination of the galaxy M87 with respect to us, probably we can observe such kind of shadows when we change the curvature left to right. But when the observer is at 90 degree inclination, so it became more effective. The most famous one. Okay. After that, when again we continue to decrease the charge, we obtain this other variety shallows. So the shallows again were divided into different distributed. And finally, when the charge is not small, the shallows resemble the structure of the cavity shallow, but this charge from here, because of the resistance of the scalar charge, they are a little bit shrinked than the shallows of the cavity constitution, because we know again from the results of value that the mass of the scalar fields impacts over the size of the shallow, and when we have scalar field, the shallows are a little bit shrinked, or can be about shrink it with respect to the size of the cavity constitution. So clearly we can observe the same thing here, and we see that if we continue to change the curvature from left to right, so the relatively small charge here doesn't lead the curvature to impacts on the shallows. And these are the conclusions here. So I said these conclusions before. But just we can make some very short overview. So the impact of the curvature really is very strong, but this impact is strong for higher values of normal charge. It's relatively strong at the middle values of charge, and when the charge is not lower, the Gaussian curvature doesn't impact so strong, or almost didn't impact all the observations, which is very nice, very clear for this. And finally, when the charge disappears, or it is not small, and both the distant and the shallows continue to resemble the behavior of this observational characteristic of the cavity, which is the thing which we assume that should be there. Thank you very much.
Thanks a lot again. So we have time for questions, if there are any. Go ahead if you have a
If we normally has a question.
Oh, I didn't have
No. Are you sure? Okay, no, I can ask a question. So you showed at some point that there were some solutions where you saw a disconnected shadow, so multiple shadows. And well, we saw this as well when we were looking at zero Gaussian curvature. And it was never absolutely clear what was the key feature in GDC relation that would actually lead to that.
Yeah.
So my question to you is, if you thought about it and if you thought of any conclusion.
So in general, I don't have scientific and precise answer to this question. So almost in the quantity which I realized that you give kind of strong impacts over this answer is this acceleration field, which was introduced from one of the papers, maybe a few, it's usually where in this acceleration field I found that if we visualize the acceleration field itself, we can see the gaps of the geodesical motion. This is what is called in the pocket papers. So we have, if we divided the three-dimensional space where the photos are distributed, these pockets can be visualized because of this acceleration fields, and to see where there is channel at which the focus removed, which we call the pockets, because they are very tiny, very widely distributed, but there is other areas which are forbidden for distribution. And I believe that this quantity is maybe will give the most kind of impact to the answer to this question. But I didn't know other mathematical instrument which can be used to give answer now. Because so why I believe it because for example, when we consider the normalized charge, it has very strongly, very difficult behavior. And it's not so easy to realize the behavior of this charge over the observation. And in addition, the Gaussian curvature became the situation more complicated. But maybe only the acceleration fields first of all can give the answer. So I didn't find other instruments which can give information. And the other thing, this because the acceleration field can be visualized for every one possible theta coordinates. So it can give the global answer to this question. So not answer related to the inclination, but the answer in general. So for the general observer, we can understand, we can observe these pockets or no. But when they're simply connected or detached one with respect to other, I'm also sure that they can give answer now.
Are there more questions?
What is the physical meaning of this parameter kappa? It's about self-interaction of the fields with scalars. How to understand the case and then.
Because this is a Gaussian curvature, so it is related to the curvature of the target space. Taken over the fields, which serve as coordinates in this space, some space on the space. So this because this probably it is related more physically to the concentration of the field itself into this into the space. Into the target space. So I don't know exactly the relation with some famous physical concepts. So I'm not so sure.
Everything I could value is a sigma model that you are seeing. It's a sigma model. And this is very, very simple because you just have a conforming fact.
Yeah.
You could actually redefine your scalar field such that the kinetic term would become canonical. And then your potential term will become different than just master. So indeed, it's a subtle direction, not canonical one. And I think it can be written like that.
Related question. O3 sigma model options by the ABM is there because it can be written this way.
So can you know
We can discuss it.
I think I also have a question. I hope it makes sense, but so to make the shadow, you need to be at a certain distance from the object, right? But is the distance that you should like outside most of the scalar field, or are you still inside some high, let's see, regions of the scalar field, or and how does it change the picture that you build?
Okay, so this is very good question. Yeah. So the same with the problem with when we consider the plasma distribution around the object. So here we did not assume that the position of the observer is in this area of space where the scalar field is enough asymptote could disappear. So we just choose, for example, for the shadow very close position is that nice 15 times the mass of the solution of the configuration of the big mass, which is very close, maybe it's very close. So in general, we didn't consider this problem, but For the operation disk, the distance is to complete time device. So it's within enough far away where the field is always zero. Yeah, so for the operation this time, I was pretty sure, yeah, probably there is no problem there. But in these cases, for the shallows, we are pretty close. Probably this will give you parts.
Thanks. Are there any questions on Zoom? Yeah, it doesn't look like
Maybe
it's,
there is one question into the chat.
I think the chat was earlier to say that they can. So, well, I think we can thank Galin again. I didn't see it today, so feel free to ask questions also later.